everyone, this is Mrs. Jackson. This is the second out of 3 videos, so part 2 out of 3 videos that is in Chapter 1, Section 2, and this entire section is focused on transformations of functions, and this second video we're specifically going to look at reflections of functions. The good news is you have a lot of experience with reflections over the x and y axis, but in this course we are going to be focused on not only doing those reflections on the coordinate plane, but looking at the effects of those reflections on the function equation itself, and also looking at some new symbolic notation to show these types of transformations. Okay, so here on an example on the coordinate plane, I have point A located at 2, 4. We're going to reflect that over the y-axis, so I'll show that maybe this way. And most of you would have no problem finding its new location, and the location would be at -2, 4. And you might not think about the exact academic definition of a reflection, but to remind you of what you should have learned in honors geometry. If I draw a segment between what's called the pre-image, so that's pre meaning before, this point A is the before transformation, we're going to notate the after transformation as A prime. So maybe we should write that down, A prime. If you did not learn that last year, I'll just review that. That's pronounced A prime, and the prime symbol is showing you the after transformation. Most of you would immediately know where to put that image at -2, 4. But the textbook definition of a reflection is this segment between the pre-image, this pre-image here, and the image. That segment is going over a perpendicular bisector, if you will. So the line of reflection, and in this case it's the y-axis, I'm going to put it in a different color. This here becomes a perpendicular bisector. So I'm going to show that as these two segments here as congruent, and I'm showing this angle here as a 90 degrees. That line of reflection is a perpendicular bisector of the segment between the image and the pre-image. So in our example, our pre-image was at 2, 4, so that's x equals 2, y equals 4, and the image or post-transformation was at -2, 4, so our x is at -2, and our y stayed at 4. So if you look at the coordinates, you could see the x is the opposite, and the y is the same. Okay, so how does that look notationally? We notate in symbols these transformations kind of as a pre and a post transformation, and we show those transformations with this arrow here. So it's kind of like function notation in a way. Whatever our coordinates x and y are pre-image coordinates, maybe let's write that. This is pre. That gets mapped to or transformed to our image coordinates, so our output after transformation. And as we just saw, if we're going over the y-axis, our x turned into the opposite and our y stayed the same. So in this case, we would show that x as an opposite using -x. Another way that this could be written is our x going in, and remember y is just f of x, that's just our function notation. So we could write that as our -x here, and the y stays the same, f of x. And finally, if we look at what this is in function notation, we have f prime of x. F prime of x, that is our image, so that's post-transformation. So our image is going to equal our pre-image with x being opposite. All of these notations take some time getting used to. Math is a language of symbols, and you need to both be able to read and write these symbols and make meaning and comprehension out of them. So I would just caution, this is going to take some time to get used to, and definitely spend some time studying this and practicing writing and reading this. Okay, let's do an example of transformation over the y-axis, a reflection over the y-axis, both graphically as well as on the function, the equation itself. So the example is graph this linear function f of x equals 2x minus 3, and we're going to limit its domain. We are going to limit it to 0, 4. Remember, this is domain, so both these values in here are x's. They're not x and y. We're going to start at x equals 0, that's our minimum, and we're going to end at x equals 4, that's our maximum. We're going to reflect f of x over the y-axis to create g of x. We're going to write the equation for g of x and see what effects this transformation has on its domain and range. Okay, so the key thing here is we're reflecting over x. Here's my little hint, what I always do myself anyway, is I do a quick little diagram of the coordinate plane, and I remind myself, if I'm going to reflect over the y-axis, my y coordinate stays the same and my x is the opposite. So I just kind of make a little diagram and I remind myself that we're opposite of x. Consequently, I use that information. I'm going to say g of x, that would be our image, equals f of opposite of x. So I've got g of x, and anywhere I see my x here in my function, my pre-image function, anywhere I see that x, I'm going to change that to its opposite. So I have 2 times negative x minus 3. So g of x equals negative 2x minus 3. Okay, let's first graph our pre-image. We have f of x equals 2x minus 3. Our slope is 2. Our y-intercept is negative 3. But we are going to limit this domain from 0 to 4. So if our y-intercept is negative 3, I'm going to start there, and then I'm going to rise and run 2 over 1, right? So I'm going to go up 2 from that y-intercept, up 2 and over 1. That's going to be my next point. I'm going to keep doing it. Rise 2 over 1. Rise 2 over 1. I'm going to do it one more time. Rise 2 over 1. And that's it. That is all I'm going to graph, because we are limiting our domain from x equals 0 to x equals 4. So let's go ahead and write that domain. Our domain, we can touch the 0 and we can touch the 4. So I'm going to use brackets. In our range, our minimum is negative 3 from a y perspective, and our maximum is positive 5. And I could touch both of those, so I'm going to be using brackets. Actually, why don't we just take a moment and write this in inequality, just so that we can put some meaning to this. So this is saying x is less than or equal to 4 and greater than or equal to 0, and y is less than or equal to 5 and greater than or equal to negative 3. So we're talking about min-max. Okay, let's go ahead and graph g of x, and we already found our equation for g of x is negative 2x minus 3. So let's go ahead and first reflect our original input. So we had negative 3 here. Actually, I'm gonna slide over here. If we go ahead and reflect this piece, we know that this is going to be an anchor here. Negative 3, 0, negative 3 is going to stay pinned there, and this point is going to end up over here. This point is going to end up over here, etc. So if we slide back over here, I think you can guess that we're going to end up with another side of a V here. So we've got a y-intercept of negative 3, and instead of rising 2, running 2, we actually have a negative slope here. negative 2 slope. And so our g of x is going to look like that. So from a domain perspective, we did have a change. Our minimum now in our domain is negative 4, and our maximum is 0. And from a range perspective, nothing's changed. So from the y perspective, we know that our y is going to stay the same. So our minimum is negative 3, and our maximum is still 5. So let's go ahead and write that. X is less than or equal to 0, greater than or equal to negative 4. We might as well write this in set notation, remember? The set of x values such that x is less than or equal to 0 and greater than or equal to negative 4. And our set of y values, our range such that y is less than or equal to 5 and greater than or equal to negative 3. Okay, let's take a look at how these transformations look over the x-axis. So we're going to reflect over the x-axis, and if we take a look at an example here, I have a pre-image A at 1, 2, and a prime post-transformation over the x-axis is going to land at 1, negative 2. Again, that line of reflection, I'm going to go ahead and draw it. The line of reflection this time is the x-axis, and that is a perpendicular bisector to the segment between the pre-image and the image. So again, our pre-image A is at 1, 2. A prime is at 1, negative 2. So x equals 1, y equals 2. And in the image, x still equals 1, and y is the opposite. So in this case, x is the same, and y turns out to be the opposite. So how does that look symbolically here? We have our inputs, our pre-image. Let's write that. This stuff is the stuff that confuses students, I found. So our pre-image goes in, and that has some kind of coordinates, x and y. And what comes out, x stays the same, and y is the opposite. So if we look at that with the function notation, we would say whatever goes in, x stays the same, and the opposite of y comes out. And then finally, in function notation, f prime of x is going to equal the opposite of f of x. Okay, so let's look at an example. This time I'm going to use an absolute value function. So we have our pre-image f of x equals the absolute value of x plus 2. And we're going to limit that domain to a minimum of 0 up to and equal to 3. We're going to reflect f of x over the x-axis this time to create g of x. We're going to write the equation of g of x, and we're going to find the effects on the domain and range for this new transformed function. Okay, so first thing I do, always, I look at what we're doing. We're going over the x-axis. I remind myself, if I'm reflecting over the x-axis, the x is the same. And what's changing is y is opposite. So I always kind of give myself that reminder. So from an equation or function point of view, that means g of x equals the opposite of f of x. In other words, the output, the y values are changing. So g of x is going to equal the opposite of, I'm going to put this in parentheses, our original function here. That means we're going to have to essentially distribute this. This is like a -1 distributing to everything inside the function here. And so I have g of x equals negative absolute value of x minus 2. Okay, so how do we graph that pre-image f of x? Remember, absolute value of x is that V shape at the origin. And if we're going to add 2 to the output, we're just going to end up having that v shift up by 2. So the new vertex is going to be 0, 2 right here. However, we were asked to limit the domain, so we're only going to graph that part of that v, the right side of that v, from a minimum of 0 up to 3. Okay, so let's go ahead and graph that. We're going to shift up 2. And unless we change anything inside of that x value and the absolute value or multiply that in the front, the slope of the sides of that v is just 1 over 1. Okay, so I'm limiting my domain here to 0, x equals 0 up to x equals 3. So I'm going to write that. And my resulting range here, I've got a minimum of 2 and a maximum of 5. And we could touch both sides, and so we're going to write that with brackets. So again, x is less than or equal to 3 and greater than or equal to 0. And y is less than or equal to 5 and greater than or equal to 2. And we probably should mark this. Okay, so if we're reflecting over the x-axis, then this 0, 2 here is going to be down here, and they're just going to get farther and farther away, right? So I'm going to move over here. I'm going to go ahead and erase those points, but we're going to move over here to the right and go ahead and graph that. So we're going to start at 0, -2. Oh, I need my pen. And our domain, we said, is x equals 0 up to x equals 3. So my g of x is going to look like this. And remember, when we're reflecting over the x-axis, our domain is not going to change. So we still have a domain from 0 to 3. Touch both sides, so we got the brackets. But this time, our output, or our y values, are opposite. So we have a minimum of -5 and a maximum of -2. And we can touch both sides. So we have brackets. So if we write that with inequalities, we've got x less than or equal to 3, greater than or equal to 0, and y less than or equal to -2, and greater than or equal to -5. Okay, let's just summarize by doing a couple of algebraic examples. The first one, write the equation of g of x by reflecting f of x, which is a quadratic, over the x-axis. So let's zoom in here. Again, remind yourself, over the x, just do a little diagram, and you can see right away y is opposite, and the x is going to stay the same. So that means g of x equals the opposite of y, opposite of f of x. So g of x equals the opposite of this entire function here. We've got x squared plus x. So we have to distribute. So we're going to end up with -x squared minus x. Okay. Next example, write the equation of h of x by reflecting f of x, which is an absolute value function, over the y-axis. So again, just quick remind yourself, over the y, draw your little diagram here. Over the y, the x is the opposite, and the y stays the same. So if we come over here then, we've got h of x equals the opposite of x. So we'll read that h of x equals f of opposite of x. So wherever you see an x in your original function, you're going to replace that with -x. So h of x equals the absolute value of 2 times -x minus 3, close your absolute value, minus 6. So h of x equals the absolute value of -2x minus 3 minus 6. Okay, 2 more examples. We've got a quadratic function here, 2x squared minus 3x plus 4. Let's reflect this function f of x over the x-axis. Let's reflect it over the y-axis. And right now, we're not looking at the graph. We're just looking this strictly algebraically. Okay, so we know that if we are going over the x, that's opposite y. Okay, so I'll call this first one g of x. So g of x equals the opposite of f of x. That's our y. So g of x equals the opposite of the whole function, 2x squared minus 3x plus 4. So g of x equals negative 2x squared plus 3x. We're changing everything to its opposite, minus 4. And if we look at that over the y-axis, we know x is opposite. So I'll call this one h of x. So we're going to have h of x equals f of the opposite of x. So wherever you see an x in your original function, you're going to replace that with negative x. So we've got 2 times negative x squared minus 3 times a negative x plus 4. H of x equals, well, negative x squared is still going to be x squared. So nothing changed here in this first term, 2x squared. However, negative 3 times a negative x, now we're going to have plus 3x. And we have our plus 4. All right, so we've looked at how to transform functions by reflecting them over both the axes, and we looked at that graphically, and we looked at that algebraically. Also embedded in this video is some key notation styles, and that tends to be more the struggle for students, so make sure you brush up on that and really dig in and do some practice problems on that notation. All right, I hope this video helps.